as you can see, this depth first search algorithm is quite generic. It needs to be specialized, and some of the methods needs to be implemented by yourself or by the solver to work. And in particular, the most important one is this one, the branching method, that is in charge of returning a set of constraints that will be the branching constraint that you will apply on each different branches under the current node. So this algorithm is recursive, okay? And a key number of operations that we need to do is, given the current node, the CSP at the current node, we need to find a branching. So we need to find a branching, which means we need to find the set of constraints that we want to apply C0 until Ck, okay? And then from a branching, we need to produce the new subnode where we will add this new branching constraint and call the recursive method to produce the next children node. And in case of backtrack, we need to be able to remove, when we come back from the child node and we need to come back and try a different one using depth first search, we need to discard this constraint that we just added. So finding a branching means that we need to select first a variable on which we want to branch, and then we need to return the set of constraints, and possibly we need to say what is the outcome. So the outcome, if you remember, you can, for instance, fail and decide there is no feasible solution, or you can say that it's an empty branching, which means that we have found a solution, okay? Or you can recursively call the branching so that you continue to explore deeper the search in the search tree. Okay, so now I will open a parenthesis, which to explain a little bit of technical details about the implementation objects that we will need to implement the different branching inside MiniCP. This is an interface that we call a functional interface. It will become clear why. This is an interface that just has one method, which is call, and this interface is intended just to execute a piece of code that you will capture, and this piece of code will be executed only when you call here, this call method. Because it's a functional interface, we can use this very nice syntactical sugar that you see here, okay, where we will capture, and this will be an implementation of our interface with an anonymous class. The body of the call method will be system out print light. So all what you see to the right of this arrow will be the body of the method. Okay. So what you get here is a new procedure. Procedure is a type of the interface, and you store into the variable myproc. At this point, it's not executed yet, so you will not see hello in the console. It will only be executed when you will call the call method of the interface procedure. Okay, and so we will use this mechanism to capture the piece of code, the fact that you will add constraint in the different nodes of the search tree. Okay, we will use this procedure interface for doing that. So the way it will work is exactly like this. You will capture the left procedure. You will not execute it yet. You capture it, and the body of this left procedure will be to post a new constraint to your model. You will, for instance, post that the queen I, qi is equal to the value v. This is for the left, the left branch procedure, and for the right branch procedure, you will capture that you will add a constraint queen of I must be different from v. And then you will store this left and the right actions inside an array of procedures. And this is this array of procedures that you will return as the branching constraints to the solver. And the solver will be in charge of doing the call on the left branch and the right branch doing the exploration. Not you, of course. Okay, this is not you as a user who will do this call. The solver will do it for you. But what you will have to do is to return this array of procedure corresponding to every k branches for the given node. So let's take one example here for the n-queens problem. For the n-queens problem, we are looking for one variable. In that case, this is the one with the first variable which is not bound. So we will iterate over every variable from 0 oops, sorry, until all the variables in Q array. Once we find one which is not yet bound, so the domain size is larger than 1, we store its index. Okay. In case there is no such variables, you just return the empty procedure, which means that you have succeeded. Okay. It's more exactly like the empty set. Okay. You just notify the solver that there is nothing else to do, and you will not generate any child node under this node. And otherwise, exactly as we have seen before, you collect the left procedure, the right procedure, and you return an array that contains the left and the right branch constraints. Okay, so this is a custom search for the n-queen problem. I will detail this further in another video just after.